Okay, so welcome everybody. A special welcome to anybody who's here for the first time. Welcome to the Madhouse, because we're trying things and things don't always work. So we're experimenting as we go, and you are the hapless victims. And I'd also like to welcome Peter from Dublin, who's giving us the talk this evening. It's very kind of him to join us on a wet Friday night from Dublin. And I'd just kick off this meeting then by saying that we are making recordings of the meeting, so just be careful what you say. So without any more, I'll move on forward to the agenda that we have tonight. Got a few notices that I would like to mention to you, followed by the main presentation with Peter. There isn't a news item this month, I should say, because Len is actually on holiday. Then Richard will do a planetarium on stellarium here for you. And then after that, we'll have refreshments and talk about things and have a look at scopes and so on. I just got to mention a few safety notices. The fire exits are left and right, and also the door that you came in at the beginning. We're testing again some ideas about how we can improve hearing, because the acoustic in this room isn't very good. And for people with hearing difficulties, it's really hard to get an intelligible signal across them. So we've got a hearing loop installed here for those that might want to use it. And we're trialing some other monitors that you can put over your head that have got a loop on for the hard of hearing. We're on Zoom, so the recording is now in progress, so be careful. I'd ask you to maybe mute all your microphones, make sure you've done that. And use the speaker view wherever possible. That's the view where you've got the speaker up in the right-hand corner, and then you can see the rest of the screen. Obviously, it's your choice as what you want to do. If we could hold questions until the very end, then we'll pick them up then from the chat and also from questions in the room. When I have got questions on chat or on the room, I'll try and repeat them so that everybody can hear the questions. Okay, so just a little bit about our society for those that are new to it. It's founded in 1968. Currently, we're 154 members. We have our monthly meetings from September to May, COVID rules permitting. And it's usually the last Friday of the month, but the advice here is always check on the website. That will have the most up-to-date information, or if you're a Facebook fan, you can find it on Facebook as well. We have our own observatory, and that's up at Flondon. Many of you know that very well. And we have used the planetarium here in the school, but at the moment, because of the COVID regulations, and we're trying to keep a regular amount of distancing, it's not really advisable to do that. So for the moment, we're having the electronic presentations here with Richard on the screen. And we have an occasional newsletter. Those of you might remember it was called a monthly newsletter, but we've now demoted it to occasional because we'll only issue it when there's something of real interest to you. And then just a little bit about our membership, which is coming up for renewal in January. It's £16 for an individual, £24 for a family. And the family isn't really limited to 2 adults, 2 kids. We're quite lenient with that. And our website, of course, SWHAS.org, a good place to go and visit to find out what's happening. Just a quick mention about this site for the new members. We are visitors here, so we have to sort of abide by the rules of the school. When you enter the site, at the main car park that's shown with a P here, sometimes we use that hall that's on the right-hand side there called the Newmark Hall. We're at the mercy of the school as to their scheduling, what events they have on. You can see their Christmas decorations all around us here, so the kids are putting on their Christmas pantomime, so we have to work around that. The barrier you know about, and then the gate, of course, with the code. You must remember that code. And we'd asked you to follow that yellow route up through the central avenue to come across to the Cadogan House Hall. It's just a one-way system that they've designated. The location of the observatory is here on the right-hand side of the screen. You can see it marked there with the yellow. And right beside it is the planetarium. So the route that we're designated for using to that is the blue route marked on that map. Or just a little bit about our own site up at it's about a quarter of a mile south of London Village. And we've got a little dome there and an 11-inch Celestron telescope on an EQ8 mount. To find it on Google Maps, the best thing to do is just search for SWHAS Observatory, and that'll give you an exact location. And if you need to get there, that's how you get. Just a quick word about our upcoming events. The next event is on December the 17th. Now, you might notice that date has changed from December the 10th, which I mentioned last time. That's to make it easier for people to attend and make as many people available to come to it as possible. So it'll be a members' images and a bring and buy. And then kicking off 2022, we'll have a talk at the end of January, the 28th of January, about the James Webb Telescope, and that's from Dr. Emma Curtis Lake. She is at the University of Hertfordshire, and she is part of the NIRCam team. I don't know if you remember, some years ago I did you a talk on JWST. NIRSPEC and NIRCam are the infrared cameras on the scope. So she'll be well placed to tell us a bit about that. Okay, so I've just had a message from Andrew saying that the people on Zoom can't see the slides. Well, not to worry, we'll remedy that very quickly. So there we go.
Yep.
I can see a few people now, so that's good. So thanks for bringing that to my attention. So James Webb Telescope, that's going to be our talk in January. So I'm going to just mention a few words about our speaker tonight, Peter. Thanks for bearing with us, Peter, while our gremlins are being sorted. There's a picture of Peter. He's the director of the Dunsink Observatory, and a little bit about his background. I think I mentioned this at the last meeting. He's a BSc Honours in Physics and Mathematics at UCD, an MSc in Optoelectronics and Image Processing. Maybe he can give us tips for the astro images here. He's a PhD in Solar Physics from Queen's, Belfast, and Senior Professor and Head of Dias Astronomy in the Astrophysics section, Adjunct Professor of Astrophysics, TCD. Peter has had some other roles that are of interest as well. He was a postdoctoral research fellow at the Solar Observatory in California, there. Senior scientist at NASA Goddard Space Flight Center. And he's a member of the ESA Solar Working Group from 2007 to 2009, and part of the ESA Space Science Advisory Committee. He also leads research into solar physics and space weather research, in particular the physics of solar storms and their impacts on Earth. So probably exciting times ahead for Peter as the solar activity increases now. So really, without any further ado, Andrew, if I could ask you to take control and give it to Peter, please. And Peter can share his presentation with us.
Thank you for the introduction, Sean. I hope everybody can hear me okay.
Yep.
Okay, good.
Okay, I'm just going to make you host, Peter.
Very good.
So
I've been back teaching this week in Trinity, lecturing, and it's my first time back in a classroom for 2 years, and it's very nice. So I haven't been on Zoom in a while. Okay, so how does that look?
Yeah, that's great. We can see that. Everybody can see that here as well. Yeah.
Yeah. All good.
Okay, very good. All right. Well, thank you so much for the invitation, Sean, and to the Society. It's always a pleasure to come and talk to enthusiasts like myself who love the night sky and also love the day sky as well, in my case. I'm going to talk a little bit about the history of the observatory that I work in, which is Dunsink Observatory in Dublin, here in Ireland. But I'm also going to talk about contemporary research as well, what we're working on at the moment, to give you a flavour for what we're interested in. I'll keep it at a high enough level, and so if you have any more technical questions, then please do ask me the hard questions at the very end, and I'll do my best to try and answer them. So this is the observatory. It actually is a very, very beautiful place to start with. The architecture is quite interesting. It's from the 1780s, and well, the main building is from the 1780s, and you'll see a dome in the front there, which contains a telescope from the mid 19th century, still in working order. The observatory has been a location for astronomical research from 1785 right up until today, and nowadays we have a number of researchers based at the observatory, and we also have people based in the city centre as well, near Trinity College Dublin. The Observatory also is a great place for people to come and visit. We have an open night once every 2 weeks during normal times, and we get about 100 people turning up to come and have a look through the telescope if it's not cloudy. But people just like coming into the dome anyway, and it's just a nice place to be, and we can talk about the telescope. Then we also have talks, visiting speakers who come in. So maybe your society could take a trip sometime, or if you are in Dublin, we're not far from Dublin Airport, please do drop us a line and come and have a look around. So I guess this story starts with this kind of scene that many are familiar with, particularly those who live outside of and away from city lights. That is the night sky. And I guess the question that we all have is, you know, what makes these stars shine? You know, when were they born? What are they made out of? When will they die? And they're the kind of questions that astronomers ask. And in order to address those questions, we have to build telescopes. In times gone by, there were facilities like Dunsink Observatory that were used to look at the stars to work out, what their composition is, how far away they are, and so on. Nowadays, of course, we build observatories that either fly on spacecraft or are at the top of mountains usually. But I guess there's a very human connection to the night sky to try and understand that all of us kind of share that curiosity about the night sky. And observatories like Dunsink are part of that story of humans trying to understand the night sky, understanding galaxies, stars, the sun, planets, and so on. And it's a very exciting time for astronomy at the moment. I often tell the undergraduates who I'm teaching, you know, when I was their age 20 years ago, I was, you know, sitting in a room, we had 9 planets. We didn't have 3,000 planets like they now have. We also didn't have gravitational waves. Gravitational waves are a thing now. They're not just a theoretical thing. Black holes were, you know, still very exotic at the time. They are still exotic, but now we have images of black holes. And also, I mean, I think one of the most breathtaking images are these images of rings, concentric rings around stars that the ALMA radio telescope has observed, which shows, you know, where planets are being formed in protoplanetary disks. So, you know, astronomy has changed dramatically over my lifetime, and I just wonder where it's going to go next. You know, what are those next discoveries going to be? And that's why we build big telescopes. That's why we've put telescopes on spacecraft. And Dunsink is one of those moments. And I'll talk a little bit about the history of the observatory to start with, and then, you know, for maybe the first half, and then the second half of the talk, I'll talk about what we're doing at the moment to look further. So this is where it really starts with this gentleman. He was the provost of Trinity College Dublin. We don't dress like that anymore, unfortunately. It looks like great fun. But Francis Andrews was the provost at Trinity College Dublin, and he went off on a tour around the continent and was really struck by the fact that there were these new observatories being built in the middle 1700s, and they were being built to discover planets. And of course, you know, the motivation for discovering planets at the time was, you know, to be famous, of course. The scientists were interested in finding new things, as we still are, and also that your king or queen or whoever it was would like to get their name put on it as well. So that was also another good motivation for it. But when he came back, he conceived as this idea of establishing a chair of astronomy and also building an observatory. Now, unfortunately, he passed away, he died, but he left £3,000, a lot of money at the time, to establish the chair and build an observatory. Now, his wife was not impressed about this, nor were his direct descendants, that he had left them. Now, he was actually quite a wealthy man, but they brought the college to court, and luckily for us, the college won, and the observatory was then built, and that's the observatory that I spend most of my time in today. So thankfully, there was common sense came out of the court process on that occasion. The observatory, these were the original plans for the observatory. It was designed by actually an English architect, and he had been influenced by, Georgian architecture at the time, of course. And so it was quite a fashionable building. And they began looking for sites. They looked south of Dublin into what's called the Wicklow Mountains, and it was just very difficult to get to at the time. They also looked north of Dublin. There's a hill called Howth Head, and Howth Head was right on the sea, and so the weather conditions weren't great. So there was a canal being built called the Royal Canal, and that was going west from the city centre, and that was only a walk out along the canal to a hill called Dunsink. And that's why it was chosen. So the weather wasn't too bad. It was easy to get to in half a day walking, or an hour on a horse, and that's why Dunsink was chosen. And then the observatory became Dunsink Observatory. Now, £3,000 may sound like a lot, but it wasn't enough, and so it ended up that those beautiful wings were never built, and that's actually the observatory that we've ended up with nowadays. It has a dome at the center, and what was interesting about this is that this was completely vibrationally isolated. So this was quite an innovation at the time, that this was set on a pier that was distinct from the foundations of the rest of the building, which meant that it was vibrationally isolated. So there was a bit of innovation at the time. The astronomer then and their family then lived on this top floor. So it was really a kind of almost a stately home. And then the downstairs there was reception rooms and also the director's office. And that was the case right from 1785 right up until 1992. So the astronomer lived in the house up until 1992. So my job did not come with accommodation, unfortunately, but I get to live in a house with underfloor heating and a heating system that works, etc., etc. So the double glazing. The observatory doesn't have things like that. The observatory was then designated effectively to be the Royal Observatory of Ireland, and I think it was King George III issued letters patent to establish a Royal Astronomer for Ireland. So as you'll be aware, there is an Astronomer Royal for England, there's an Astronomer Royal for Scotland, and there's also there was a Royal Astronomer for Ireland right up until 1921. But the first Royal Astronomer was John Brinkley, and John was quite distinguished during his career and made some pretty interesting discoveries. He was born in England in 1763 or 1766. They're not quite sure when he was born, and there's an interesting story around his birth. They're not entirely sure who his father was, which was quite interesting at the time. And for a man who went on to become the Royal Astronomer of Ireland and then a bishop, having such an interesting birth wasn't always good for your career in those days. But he became an expert at building instruments, and he made detailed astronomical measurements at Dunsink. In fact, his transit book is still in my office, and it's bound in vellum, and there's meticulous records of stellar positions. Of course, at the time, people were obsessed with using parallax to try and estimate the distances to the stars. And in order to do that, you needed a telescope, of course. And so this is the telescope that was located in the observatory. These pillars here are called the Meridian pillars. They're Portland stone. And then there's a telescope here. And the astronomer would look through this and then look at the transit of stars, and they would be able to then work out the time that they passed overhead and also their elevation or their declination. And you could work out, well, time between Dublin and London, it was 24 minutes and 21 seconds. You could work out longitude, and you could then work out things like parallax and try and estimate distances to the stars. These are an example of some of his records, just to show you, this is late 1700s. I'm not sure what date this one is at. This might be 1800. But, you know, these are the kind of observations that he was making. And this was very much international science at the time. You know, he's making comparisons with Greenwich, with Palermo in Italy, and making observations of the positions of stars. Now, what they were expecting to see was that stars that were more close, that were closer, would move a little bit over a 6-month period. So if you looked at one, say in March, you'd measure positions, and then 6 months after March, you'd again look at the same star field, and the closer stars would appear to move slightly, and that's the parallax effect. And many people were doing that. And if you could get that parallax effect, you could then measure a distance to a star. Now, he did this with great accuracy. He published his results, and he won the gold medal, the Copley Medal, actually, it's called, of the Royal Society for this, making this. Now, the Astronomer Royal for England then went to try and test this and didn't have equipment that was sufficient at the time, but eventually did get observations that were sufficient to test Brinkley's observations to find out that actually Brinkley was incorrect. And this was a real traumatic incident for Brinkley in his career, that he'd been proved incorrect by Pond was the name of the astronomer. You can see Mr. Pond referred to down here. But anyway, he was incorrect. And this is one of the reasons why we think that Dr. Brinkley disappeared from Dunsink and became a bishop. There's also a fact that the bishop was paid more than the royal astronomer. So there may have been a number of factors in his decision to leave. If we jump forward, after Brinkley, the next royal astronomer was Sir William Rowan Hamilton. And Hamilton really was a child prodigy. He was speaking about 8 languages by the age of 12 years old. He was winning international mathematics competitions, and was entered Trinity College Dublin. And depressing for many of us who are professional astronomers, he was made the director of Dunsink Observatory and a full professor at the age of 21. Most of us haven't even finished college at that point. But anyway, he was made the royal astronomer at the age of 21. He was so brilliant. He is world renowned at this point. Anybody who studies physics, mathematics, engineering, chemistry around the world will know of the Hamiltonian, which was named after Sir William Rowan Hamilton. He worked on optics. He made predictions of how light moves through crystals, but he's particularly famous for discovering, I guess is the only word I can think of, these things called quaternions. Now, quaternions is a quaternion is a vector. In fact, he coined the word vector, and he also coined the word scalar as well. They're both due to William Rowan Hamilton. And a quaternion has both a scalar and a vector. But normally with a scalar, it's just a point, it's just a number. But a vector tells you a direction. So if you want to work out a velocity, you know, say my car was traveling at 50 kilometers per second to the west. That's a vector. But his quaternions allowed him to take into account rotation as well. Now, not that you want your car to be doing a rotation, but if it did rotate, then you could describe it with a quaternion. And this was complete revelation, and he had to invent a whole new algebra to do this. And it has great use nowadays. It's used in computer games. Anybody interested in 3D computer games, or quaternions are used to handle a lot of the 3D rotations that are going on in computer games, and also in space travel and satellite control. He made this discovery actually while walking along the banks of the Royal Canal in Dublin. He was on his way into the academy in Dublin, and he had this flash of brilliance. He said it was like a circuit closing in my mind, and a flash of brilliance sprang forth, I think is what he said. And he was worried that he'd forget it. So he took out his penknife and scratched it into the wall of Broome Bridge in Cabra. And unfortunately, it's not there anymore. It was weathered away. But his wife looked blessed and impressed in this photograph. But that's where every year we have a walk on October the 16th. We walk from the observatory down there to pay homage to this discovery that Hamilton made. So that's Broom Bridge in Cabra. And here's his original handwriting in his notebook. So he also wrote the Quaternions into his notebook. So here's I squared equals J squared equals K squared equals -1. And here's some of the algebra. And then here's him trying to work out how they're going to be used. And so this is from the mid 1800s. Hamilton may have been a good mathematician and a good kind of mathematical physicist, but he was no astronomer, and he didn't particularly like doing nighttime astronomy. In fact, some of his notebooks were kept by assistants, and his sister as well, Elizabeth, was also involved in taking observations. Now, there was a very wealthy man at the time, actually also, I think he was from London, his name was Sir James South. And South bought himself a very fancy lens from Cachua, a company in Paris. This is a 12-inch or 30-centimeter achromatic doublet lens, and sent it over to Trinity saying, you know, congratulations on X, Y, and Z, and here's a beautiful lens which will help at your observatory, but you're not to give it to William Rowan Hamilton because that man will break it. What a thing to say, but he handed over this lens. And it was only after Hamilton died that the observatory then built a telescope to hold this lens. Now, this is one of the original drawings. This was, and it was built in Dublin by a company called the Grubb company, and Thomas Grubb went on to make telescopes that, you know, the Anglo-Australian telescope was made by a Grubb company. So they operated for well over 100 years, and they became very wealthy during the First World War when they were making gun sights and periscopes and the like. But they were also experts at making telescopes, and this telescope is still in the observatory, and we call it the South Telescope. It's very confusing because it's not in the south. It's actually east of the main observatory, but it's named after Sir James South. And it's still the largest refracting telescope in Ireland. It's working perfectly. This is a photograph that I took with my iPhone a couple of days ago. And I like the fact that it's a mobile phone from 2018, taken through the Grubb telescope that was built in 1868. Just a couple of days ago. But with your eye, you could clearly see the bands on Jupiter, but also here are 3 of the moons that orbit Jupiter. So this is, oh God, which is it? Well, Io was in front of the disk, but there's also Callisto and Ganymede and Europa are the 3 moons that you can see there. So actually, if you go out, well, it's raining over there, I believe, at the moment. If you go out tomorrow night or the next night, you can see Jupiter. If you look off to the south or the south west, you should see Jupiter in the night sky. It's actually been pretty spectacular. You can see Venus just after sunset, and then Saturn, and then Jupiter in the night sky. So definitely worth a look out. The observatory was also, like many observatories, was also responsible for setting time in Ireland. And so Dublin Mean Time was set at the observatory from the transit of stars in the same way that Greenwich was. So there was a meridian that passed through Dunsink, and it was 24 minutes or 25 minutes and 21 seconds off GMT. And there's a ball, actually, there was a time ball in the very center of Dublin City, just beside O'Connell Bridge on the River Liffey, and you can just see it there. But that time ball would drop at 1 GMT every single day, which caused great confusion to the people of Dublin because they weren't working on GMT, but the mariners were. So mariners would set their clocks and off they would go from the River Liffey off round the world. But they'd set their time on this. But they also sent a time signal into the central bank, which is just down the road here, so that financial transactions were carried out accurately. And James Joyce also was quite interested in these. He was interested in parallax. He was interested in time. And this is just a quote from his book Ulysses, where he says, "Time ball on the ballast house is down, Dunsink time. In fact, he was wrong in this case, and he goes to argue about the difference between GMT and Dublin Mean Time as well later on in that paragraph. So well worth a look. Okay, so we're going to jump forward, not 50 years, we're going to jump forward over 100 years to what we do nowadays. Nowadays, the observatory is run by an institute called the Dublin Institute for Advanced Studies, and it was formed in the 1940s by Eamon de Valera. And what Eamon de Valera had spotted was there was a lot of great physicists and trying to escape from the continent during the Second World War. And the first person he attracted to the institute was Erwin Schrödinger. So Schrödinger moved to Dublin and lived in Dublin for 15 years with his wife and others. I can talk about that later on. And so the institute was formed really around Schrödinger. There was other schools formed as well. There was one in geophysics, there was one in astrophysics, there was one in theoretical physics, and there was also a school of Celtic studies as well. But in science, it was geophysics, theoretical physics, and astrophysics. Nowadays, we have about 110 people working in DIAS on all these kind of fundamental problems. And in astrophysics, there's about 40 of us working mainly on observational astronomy. I heard you mention the James Webb Space Telescope. I'm sure lots of you are following that project with interest for far too long. And you've probably spotted that the launch has been delayed until after December the 22nd. There was some last minute changes. We were hoping that it was going to be launched very, very soon, but it's anyway, we can wait another month. That's fine. It'll be late December before it is launched. We're also involved in the European Southern Observatory in Chile that has a number of very large telescopes, which I'm sure some of you in the audience have heard about before. And we're also interested in radio astronomy as well. I'm head of this radio telescope here. It looks like a weird telescope, but I'm going to spend some time talking about that as well during the talk. We're also involved in Solar Orbiter. I'm one of the scientists involved in this Solar Orbiter spacecraft, which was launched in February of 2019 or 2020? God, I should know. I was at the launch. It was my last international trip to Florida. And we're also involved in gamma ray telescopes. This is HESS, which looks at high energy gamma ray air showers that's in Namibia in Africa. So I'm a solar physicist, and so what I really care about is the sun and solar activity. So I'm using this spacecraft here called Solar Orbiter and this radio telescope here. So I'm going to focus the rest of the talk now on these pieces of equipment and then the kind of science that we're trying to do with them. So this is just a wonderful movie that was from a couple of years ago, and it shows really what I've spent the past 20 years working on. This is an extreme ultraviolet, almost X-ray movie of the sun, and it shows you the sun's atmosphere, which we call the corona. And you can see there's all these small little bright areas which are called bright points, but there's bigger areas here which are called active regions, and these sit above sunspots. But from time to time you can get explosions, which is what happens over here. This explosion here is called, well, the brightening is called a solar flare, and the eruption is called a coronal mass ejection. And what we're really interested in is trying to understand the basic physics of these phenomena. And if we understand the basic physics of these phenomena, we can better forecast them. And we care about that because once these objects, or once these storms are launched off the sun, they can come barreling through space and hit the Earth. And the nice consequence of that is we get the aurora borealis. So within 1 to 3 days, one of these solar storms can hit the Earth to produce the northern lights. So one of the things that we like to try and do is forecast when the solar when when the aurora borealis might be visible. But there's also a downside to that when you've got energetic protons barreling through space and they hit a spacecraft. Electronics don't like energetic protons, so you can get problems with spacecraft electronics, with GPS systems, and even with the power grid here on Earth. You can also get adverse impacts. So there's a real applied aspect to the kind of research that we do. We make these observations with both ground-based facilities and with space-based facilities. The one that was launched in February of 2020 is called Solar Orbiter. That was, as I said, my last international trip. I flew over to Cape Kennedy, or to Kennedy Space Center in Florida, and we saw an Atlas V rocket lift off at nighttime launch to take this out into space. Just quite an amazing experience. The only launch I've actually ever been to. But it was sent on quite an amazing journey. So as you can see, it departed the Earth and very quickly did a gravity assist, and then ended up being brought into an elliptical orbit. And here's another gravity assist. Oh no, sorry, excuse me. I didn't mean to do that. Let's do that again. Okay, there it is, being launched from, I'll just leave it alone actually. And it goes into an elliptical orbit about the sun. And the point of these gravity assists as it passes by, say, the Venus there in December 2020, is to try and bring it closer and closer and closer. And then it does another Venus gravity assist in August 2021. And then it's doing a flyby of Earth. And you'll just have noticed that there, that the date of that is tomorrow morning. Am I right with that? 26th. Tomorrow morning actually is the date. This is actually just, it's 4 UT tomorrow morning. So this movie is a bit out of date, but tomorrow morning at 4 UT, Solar Orbiter will pass the Earth, and that will bring it into an even tighter orbit with the sun. Eventually it'll get inside the orbit of Mercury, and once it's inside the orbit of Mercury in March, we're going to get the closest pictures ever taken of the surface of the sun. So that'll give heliophysicists a real new insight into the workings of what's going on in the sun. It doesn't only have cameras on board, though. It also has other instruments that measure densities, temperatures, magnetic fields of the wind from the sun and solar storms from the sun. And here is the spacecraft itself, or an artist's impression of the spacecraft. But the instruments, the scientific instruments here, are peeking out through little apertures. And actually the spacecraft is going to suffer extremely high temperatures, hundreds of degrees Celsius on the sunward side of the spacecraft. But you'll notice that there is a black coating on it, and that's called solar black. And it was actually an Irish company called NBio who came up with this coating technology. They won the contract from the European Space Agency. The rest of the spacecraft was built actually in the UK, now that I think about it, but then assembled by the European Space Agency and launched by NASA. So really very much an international journey. And as I mentioned, tomorrow, quite incredibly, very suitably for this, it will be on the 27th of November. It'll at 4 UTC, it'll be 640 kilometers above the Earth. So that's really, really close for a spacecraft that's traveling at kilometers per second is the best way of quoting its speed. So it's traveling at immense speeds, and it's a worrying time for us in the team. Number one, it's getting close to the Earth, but number two, it's going to pass by within low Earth orbit. And as you have seen recently, there was some tests that have left an increased amount of debris. Now simulations have been done, and it's about 1 in a billion chance of us being hit by anything, but there is still a non-zero chance of the spacecraft. So it'll be nervous times for me. You can have a look at, if you want to watch in real time, just have a look at Twitter, and ESA operations have a Twitter handle, and they'll be tweeting as the spacecraft approaches. And if there's a dearth of tweets, I'll be nervous. But anyway, that's so Solar Orbiter will come in If the 26, if the collision probability is high enough, maneuver performed. So we haven't heard anything today, but tomorrow then it'll go in, make its closest approach to the Earth, and then fly out on its way back in to the sun. And then in March, we'll begin prime science activities. So exciting times, and I'm sure you can get somebody from maybe University College London to come down from MSSL to give you a talk about that, maybe in person, because there'll be they were involved in building some of the instruments on board. Okay. Another instrument that I've been very much involved in is called the Low Frequency Array. This is also being used to study the sun, but also other astronomical observatories. The telescope itself is a little bit weird, I guess, in that it is actually a network of radio telescopes that stretch from Eastern Europe here over in Poland and Latvia, right in through Germany, down to France, and primarily based in the Netherlands, then on up to Sweden, into the United Kingdom, into Chilbolton, and then out to Burr. Now, 5 years ago, we were not part of the network, and eventually convinced our government that this would be a great idea to join a telescope that was the biggest low-frequency radio telescope in the world. But also by building one a site in Ireland, we'd make the telescope 2,000 kilometers wide. And as you know, bigger telescopes allow you to see smaller things, but bigger telescopes allow you to also see fainter things. So by building a radio telescope in Ireland, we were able to extend the capabilities of this European network of radio telescopes. Now, radio telescopes don't like wind farms, they don't like airports, they don't like mobile phones, they don't like radio noise, and so you've got to build them in remote locations. So in Ireland, most of us live around the coast. It's either in Belfast or Dublin or Cork or Limerick or Galway, and so in the centre of Ireland is quite flat, and it's quite underpopulated relative to the coastlines. So our immediate idea was to go into the Midlands and see if we could find a location. Of course, anybody who knows Ireland knows that Burr was a global centre for astronomy in the middle of the 1800s. And this is the third Earl of Ross. His descendants still live in Burr Castle. You can go and visit. And he built this amazing telescope called the Leviathan Telescope. It was 1.8 meters in diameter at the bottom where the mirror is, which is 6 feet in diameter, and then 52 feet or 16 meters long. And the observer would hop up here and make observations. And he made great discoveries with this. He was the first person, and it's quite incredible. Imagine training your telescope and being the very first person to see something that no other human being had ever seen before. And he was the person who first saw spiral arms in galaxies. We didn't know that there were spiral arms in nebulae at the time. Herschel had built his telescope, but it wasn't big enough to see, to resolve any structure within these nebulae. But Ross saw them with his great telescope. There's a great story behind that. He had a little bit of money, but his wife was even richer. So between the two of them, they were able to build this great telescope. And this is a contemporary picture. This is what it looks like nowadays. And you can just see that he captured very well the spiral structure. This is called M51, the Whirlpool Galaxy. And you can see that he captured quite well the spiral structure. This is an image taken by the Hubble Space Telescope. So what does an international low-far telescope station look like? Well, this is one taken from a hot air balloon. But what you can see is this is about 2 football fields or 2 rugby fields. And what you can see is here are the low band antennas and here are the high band antennas. And then here's a control room over here. And what it does is it picks up radio waves between the frequencies of about 10 megahertz, which is below FM radio, right up until 240 megahertz, which is above FM radio. And underneath all of these tarpaulin covers are lots and lots of antennas. And they're cheap things. But the thing about being cheap is you can build 10,000 of them and spread them across Europe. And that's what we've done. So the total network is about 200 million euros of investment to build this radio telescope. And it's giving us sensitivity, it's giving us spatial resolution in a way that no other low frequency radio telescope is currently doing. Now, we built this in 2017. We hired 24 undergraduate students and a contracting company, and they all lived in Birr for 3 months in a kind of a social experiment in a house almost. And every day they came and they built a telescope, which is a really great experience for these students. And many have gone on to do PhDs and master's degrees as a result. And so this is the telescope. Very nervous when we went to turn it on. You know, is smoke going to come out of the cabinet here where all the electronics are? Have we connected up all the cables? There's over 400 cables coming out of here. Did we get them all right? And we turned on the telescope and started trying to make an image of the sky above us. And so this was the first image that we were able to get. There was no smoke, I'm afraid, which was a great relief to all of us. But we were able to see that there was something that looked familiar above us in Birr. And what you can see here is, this is actually the Milky Way that you're seeing here. This is radio emission coming from the Milky Way. And these two objects as well were familiar to us as well. So we overlaid it with some software, and you can see that Cygnus A, which is a radio galaxy, was exactly where it was meant to be, and Cassiopeia A, which is a supernova remnant, was also exactly where it was supposed to be. So great result for us. There was a few bottles of Prosecco opened that night, and a few beers drank as well. So it was great celebrations. And I was working on this for 10 years. So to see this was quite an emotional moment for myself, I have to say. So this was in July 2017. But that's only just the Irish telescope. And in the United Kingdom, you can do exactly the same. For a scientist, that's good. It was very satisfying personally for me, but it's actually in working in international cooperation that it really shows its strength. So what we did then was join up with the International Telescope, and we then are able to zoom in on this object here. When you zoom in, this is what you see. Quite incredible. And this is, I just showed you there, this is Cygnus A, which is radio galaxy. And what's at the center of this is a black hole with all of this X-ray emitting gas around it. But these jets here are what the radio telescope sees. And it sees these jets of hot gas moving out at light speeds from a black hole. And so without a large telescope, you just can't get the resolution to see this. And without a large telescope with lots of antennas, you're just not able to see the structure in these jets of material. Of course, the first thing I wanted to do was also have a look at the sun. And this was some work that I did with my graduate student here, Diana Morrison. And we turned the telescope at the sun and just to see what we could see. And this may look like noise to many people, but what we're seeing is lots of pops. It's individual little bursts that are happening on the sun constantly. And they're associated with the acceleration of electrons. But you don't just see that there's lots of this kind of radio noise coming from the sun. With the telescope, you can actually take images and you can say, oh, there was an explosion that accelerated electrons that produced radio waves, and it happened here. So what it's showing here is there's a big explosion here, launching a coronal mass ejection, and then also accelerating electrons and producing these radio waves. And this is a paper that we published in Nature Astronomy, which is just really satisfying that our first paper that came out with the Irish Radio Telescope was published in Nature Astronomy. And Diana is now a research fellow in Finland, still working on similar kinds of things. Okay, what else did we look at? Of course, we couldn't, when you build a radio telescope, you've got to look at pulsars. You all know the story of Jocelyn Bell Burnell from County Armagh, who went to Cambridge and was involved in building a radio telescope there, which went and discovered pulsars. But of course, with our radio telescope, we then pointed it at some known pulsars. And what did we see? Blip, 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 periodic pulsations. So we were able to, we were able to get our software working that pointed the telescope, that then picked out one of these pulsars. And a pulsar is incredible. You know, they're only about 10 kilometers across, and they're rotating many times per second, sometimes thousands of times per second. So a 10-kilometer wide object rotating so quickly is just quite incredible. But they produce a beam of electrons and a beam of light and a beam of radio waves. And it's that beam of radio waves that the radio telescope works out or picks up. So it's kind of like a lighthouse swinging around, and the telescope picks that up. So that was a great, it's great to be able to see that. And now we're surveying lots of pulsars, and sometimes they glitch. They don't always tick as you might expect. And those glitches are really interesting. Why is there a glitch in a pulsar? One of my PhD students, David McKenna, is working on that problem at the moment. And the thing about having your own radio telescope is when it's not being used as part of the international network, you can go, oh, thank you very much, we'll take that, and point at a lot of other objects ourselves. So he's looking at those. And also there's some giant pulses. We've been looking at the Crab Nebula recently. Actually, the crab was named by the third Earl of Ross and Burr as well. He thought it looked like a crab, hence the name. But we're looking at the crab, and it shows these giant pulses, and we're trying to understand what's going on there. Of course, we had to look at the Whirlpool galaxy as well. And this is what the Leviathan telescope saw in the 1840s. And this is the third Earl's sketch showing the spiral arms and the two interacting galaxies. But LOFAR then tells us even more. LOFAR tells us about the magnetic fields that thread the galaxy and control the way matter moves. And it can also be used to work out densities and temperatures. And it shows you the spatial distribution of those. So you can learn an awful lot with a radio telescope. You can also zoom in on particular regions in spiral arms, or in our own galaxy. You can look at objects in our own spiral arms and look for things like this. And, you know, we've all seen that picture on the front page of our newspapers last year when the EHT saw the black hole. But it kind of was I felt it was a little bit of a disappointment when I saw it. Well, I was blown away, okay? I was blown away, but the context was hard to get, even for an astrophysicist. And it's only with other telescopes that you can get the context. If you zoom out from that, it turns out that that black hole is embedded in a jet of material. And this is with the VLA, the Very Large Array Telescope, that only saw these jets. And then if you zoom out even more, the VLA sees that there's an envelope of hot gas around it. And this is at 1.5 gigahertz, so that's microwave frequencies. And if you zoom out even more, you find that the whole thing is embedded in a huge, big, hot blob of gas. And that's what LOFAR sees. So LOFAR sees this hot blob of gas, and with each different telescope with different baselines, you can see different resolutions. So LOFAR is a telescope the size of Europe that sees this. And then this telescope here is one that's basically it has a baseline that, you know, goes across continents from the United States to Europe, and is able to see these resolutions here. So you can see, what is that, 0.00001 arc seconds, where LOFAR can see 100 arc seconds, but we see the biggest feature. And then you can understand that inside here there's a black hole, and then there's a jet of material outside it, but all of that sits inside this. That was really where it was formed and what it was gushing from. You may have seen also recently that there's, and I wanted to show you this image, I just couldn't resist. There is, it's not really an image, it's a bit of a combination of a model and an image, but just to show you, there have been advancements on that black hole image, that you can see all of this kind of wispy material, which is magnetic field lines threading the event horizon of this telescope. So here's the black hole, and here's light that's bent around the black hole, and you can see then there's increased resolution around it. So with that, I've given you a whirlwind tour, and I'd like to just show you some of the people that work on all this exciting stuff. We're from all around the world, based at Dunsink and in the city centre. There's people from Russia, Italy, UK, France, Armenia, I see somebody there, all working together on some of these great projects, and it's a pleasure to be part of these projects and have the honor of working with these people. And so with that, I'll thank you very much for your time, and I'm happy to take a few questions.
Thanks very much for that, Peter. That's a very, very interesting range of topics that you covered there. And we thank you very much for that. So can we show a round of applause for Peter, please? Right, okay, so if there are any questions, now is a good time to ask. So let's just look to the Zoom participants first. Anybody got anything from Zoom? Okay, don't see anything so far on the chat. From the audience, any questions from the audience? I found the whole thing very interesting, but the LOFAR aspects of it must open up a whole new area for you, because Ireland isn't known for its extremely good, stable atmosphere for viewing optically in the astronomy circles. So how much do you think LOFAR has actually contributed to boosting that sort of side of physics?
Yeah, I mean, you know, in Britain or Ireland, it's not the place to do optical astronomy. Actually, most of Europe isn't good either. So yeah, you got to go to the Canary Islands or Hawaii or so on. But at radio wavelengths, we don't care about clouds, you know, and we don't care about snow. We care about lightning. Lightning isn't good, but we don't get much of that either. So it's just, you know, it's a great place to do astronomy. In fact, you know, because we don't have significant military, and because we don't have airports in that area, we've actually got the most radio quiet site in Europe in the LOFAR network. So all of the other telescopes suffer from radio frequency interference. We don't so much. We also don't have DAB radio. We've just turned off DAB radio. It just never became popular. And so we don't have DAB radio interfering at either, which is great. The one challenge for us is going to be wind turbines. It's a flat area of the country, so it's a nice place for controlled airflow and wind flow. So wind turbines aren't great for us. The blades spin, they reflect radio waves, and they have a motor that also, or not a motor, a generator that can emit radio waves. So that's our one challenge. So we've asked for an exclusion zone around the telescope of about 10 kilometers to try and keep them away. You know, there's plenty of other places that they can build their wind turbines. So that's our one challenge at the moment.
Great, thank you. Any other questions from the audience? Everybody's incredibly well behaved tonight. Okay.
Oh, there must be a kid there. Is there any kids there? Are there any kids there?
No kids.
No kids.
Except old kids.
Because it's usually the kids who have a nice hard questions about aliens or something.
Is there any way we can follow what is being carried out on the sun cameras? Right. The question is, Peter, is there any way we can follow what's been carried out with the ESO solar orbiter? Is it? Yeah.
Yeah.
You mentioned Twitter. Yeah.
Yeah, so if you on Twitter, you can go to ESA Solar Orbiter. You'll find it there, ESA Solar Orbiter, all one word, and you'll find out exactly what's going on there. European Space Agency's website as well. If you go to esa.int, so that's int/solar orbiter, you can find out what's going on. But Twitter tomorrow, well, tonight and tomorrow is where to follow that Earth flyby. Then in March of next year, when the new science results are coming, again, Twitter is probably a good place to keep an eye on it.
Okay, thanks for that. Any other questions then? Okay, there's one more. Jared?
That protective stuff on the solar orbiter, why is that black?
Okay, so the question is, why is the protective paint on the solar orbiter black?
Yeah, it's a, you would think that you would be better off with like a foil that would reflect the heat. It wasn't very clear in that, but the way it works is there's actually a gap. There's the black foil which absorbs the radiation, and then there are radiators that radiate out on the other sides of the spacecraft. So that's it's just a kind of a slightly different way of reflecting the light, and maybe not reflecting is a bad use of the word, but it absorbs it and then re-radiates it in a slightly different manner. So the point is, you want to absorb the light, and then you want to absorb it and then re-radiate out the sides. If you have a look at the Solar Orbiter website, you can see that there's this kind of lattice work that then re-radiates. And it's actually made from it's a ceramic material, which is really weird. It's crushed burned bone that is then used and formed into a paste, and it had really good thermal properties. In fact, the company used to be using it for prosthetic limbs, was what it was originally designed for, and then they found that it had very interesting thermal properties.
Okay, thanks. Any other questions then? If not,
Yeah.
we'll
Peter.
one more. Sorry.
Yeah, I was going to say, Peter.
What's the timeline of the actual satellite? How long is it expected to be on this mission?
So the question here, Peter, is what is the timeline for the solar orbiter to be online?
Never ask a scientist how long do you want the spacecraft to be up for. The answer is, you know, I'm just going to give you an example. The first spacecraft I worked on was called SOHO, which was launched in 1995, and it's still going up there, and it was only meant to be a 5-year mission. So, you know, if we can, you know, Europe has spent over €1 billion on this. It has a nominal, and you'll see here, we're going to go 2020, 2021. So, you know, nominally 5 years, but hopefully 10. You know, there's no reason why it couldn't go 10 years. But, you know, it's funded at the moment to about 5. And, you know, it all comes down to funding. You know, getting data down is expensive. That's one of the things. You know, it's the operations, and getting the data down is pricey. So, okay. Okay.
Any more then? Okay, with that then, I'll just thank you once more, Peter, for a very interesting talk covering a huge range of topics. Thanks again. And so if we now, Andrew, if I could ask you to return host back to me, and we'll get Richard on to do the planetarium software.
Okay, thank you.
Right. And actually, Sean, at this point, I'll bid you farewell as well. It's a very important night here in Ireland, because it's the Late Toy Show. So this is a big family event every year. The Late has been running for, I don't know, 50 years. Sean will know it very well. But every year they have a toy show where all the families get together and all the kids stay up late and eat popcorn. So my kids are downstairs, so I'm going to have to go and join them. And thank you very much for the invitation.
Yeah, thank you very much for taking the time out to visit us, Peter. Thank you. Bye.
You're very welcome, and thank you for the invitation.
Well, good evening. One of the things that interested me about that talk was the fact that I have a very old book. It goes back to 1890 that I bought 50 odd years ago in a second-hand bookshop in West London, and it's called The Story of the Heavens, and it's by Sir Robert Ball. Now, he worked at Dunsink Observatory for quite a few years, and in his book he talks about the transit of Venus that occurred in December 1882, I think it was, that he observed from the domes at Dunsink, and the fact that they were actually trying at that time to use the transit to do something really quite remarkable. They were trying to time the actual point at which Venus enters the sun's disk and when it leaves, and compare it with other people's observations to end up with something that will give you, amazingly enough, a scale of the solar system of distances, so that having got the distance to Venus, you can work out all the other distances. Now, of course, it's done much easier by using radar. Anyway, the point is that they were observing this, and it was snowing. And what they actually saw when the sun came out at 1 o'clock out of the clouds, they saw a lot of streamy, sparkling lights floating about, which was, of course, the sun reflecting off of the snowflakes. But at the end of his thing, he says that no one will see this sight until the summer blooms in 2004. And I thought of that when I was observing it. I thought, all that long time ago, he wrote something that I'm actually seeing. So just a connection with Dunsink that we're talking about. Right, now, what I'm going to do, I'm going to move a little bit. I'm going to move to the east. Do this, let's see. Trepidation, move south. Come to the east. Now, one of the first things that we see in the sky as the sun has set and in the east is this star here, this star Capella, which is rising as the sun sets. By mid-evening, it's very well high in the sky, and by midnight, it's virtually overhead. Now, it's a yellowish star. It's actually a combination of two stars, two F-type stars, that are actually, so it's actually a multiple system. But that star occupies the same spot, or more or less, that Vega holds during the summer, which is, of course, a blue-white star. It's a type A star. It's just interesting that these two stars sort of share this thing. One presides over the summer, and the other presides over the winter. And you can tell it's Capella because you've got this little triangle of stars here that are the kids. One of them, I forget which one, is actually the mystery star Epsilon Aurigae, which is a star that is actually involved with a cloud of dark matter, not dark matter, but matter that's not illuminated, that periodically covers it. And so its light curve actually varies considerably, but it's on quite a long time scale. It's so many years between eclipses, and then you get this weird sort of eclipse that flutters and flutters and flutters, and it's taken astronomers an awful lot of work to realise what exactly it is. And it's taken, I think at the last time, which was in the 1990s, they actually worked out using all different wavelengths of telescopes, multiple international observation, to actually prove that this was actually, this was what was causing it, this cloud of matter that was rotating around the star. So there's a few mysteries in that particular area, particularly with Epsilon. Now, one of the things that Auriga is actually well known for, and is probably the main thing that people could point out, is the fact that there are three very, very attractive clusters of stars, and in fact you can see them on this thing here. You should be able to see some little misty patches here. They are three clusters. They're on Messier's list. They're M36, M37, and M38. Now you can see them very well in binoculars. In fact, in binoculars, if you've got fairly wide angle ones, you can actually see them all at the same time. But individually, they have different characteristics. M36 is quite a sparkly cluster, but there aren't a lot of stars in it. And you quickly, it's nice to look at, but it's just a few spangly stars. M37 is a dim, misty patch, which when you look at closely, you can see individual stars in. So it's much more subtle. It doesn't sort of shout, it just sort of sits there. And that is followed by M38, which is actually a combination between the two. The star's not so bright as M36, but they're arranged in a cruciform shape, and there's a faint sort of mist of stars in the area. They're all worth looking at, whether you use binoculars or use a telescope. They're certainly pretty good, and they're really quite easy to see, even with the conditions that we're in at the moment, with the light pollution and the general sort of murkiness of our skies. They stand out quite well, and it's certainly in binoculars they're much easier to see than you'd think. But they're sort of located in this area here, this stream coming down to Taurus. Now, I'm pretty sure I mentioned last month I mentioned this star here is actually not. It's actually a star that's disputed because it actually belongs to Auriga and it belongs to Taurus. Its name is El Nath, which in Arabic is the butting one. So you'd think actually it belongs to Taurus, really. After all, if you include it with Auriga, then we've got a bull with one horn, and that's a unicorn. So, you know, you've got to have both horns, really. Now, we're coming up for the time of year when this constellation here, which obviously most people can identify quite easily, which of course is Orion, that is rising in the sky, and by mid-evening it's reasonably high in the eastern sky at the moment. Now, the interesting thing about that, let's get rid of that. Don't need to see that. Although November, they're nice. It's not a particularly easy meteor shower to see, actually, and I have tried. It's rather sparse. Anyway, getting back to the main point. Now, Orion is made of very giant stars. Of course, Betelgeuse is a red giant, which means it's pretty big. In fact, if you put it where the sun is, it would encompass most of the planets. Well, certainly out as far as Mars. So that's pretty big. It's not very dense, though. The outer layers are quite tenuous, and in fact, it probably isn't even approximately globular in shape. It's probably quite a misshapen sort of shape, not like a star at all. Anyway, that's usually our main port of call when we first look at the constellation. It's nice to see the colour, etc. And then you notice that there's these other stars. Now, the other ones are all A-type stars or B-type stars. They're hot stars, and they are much more distant than Betelgeuse. Betelgeuse is relatively close. So the rest of the constellation is a long way behind, or in the background, to Betelgeuse itself. Of course, we've got our famous belt stars here, which are lead us to Sirius, which at the moment is below the horizon. And you've got Rigel here, which is a blue-white star. Now, that is much more distant. In fact, it's been very difficult for astronomers to get an accurate distance. It's certainly thought to be something like 900 to 1,000 light years distant. So in real terms, it's much more powerful than Betelgeuse. It also has a companion, a little star that sits on the side, and that is quite easy to see in a small telescope. It's not really that easy to see. You do have to concentrate a little bit, but it's worth having a look at. And even further, when we come down, we've got, believe it or not, this hunter. He might be hunting, when in fact he's not hunting. What he's doing is chasing the Pleiades, because he's a hunter that's actually hunting women. So it seems, not animals in that sense. He's said to be chasing the Pleiades, which are running away from him. And of course, he's never going to catch them because well, he can't do it anyway because he's running and they're going at the same speed. Anyway, the fact is that in reality that he's standing on top of a hare. The hare is Lepus, and that's this little constellation underneath. In fact, if I see if I can get the constellation figures up. There's Lepus down here. That is the hare. I must admit, it looks a bit more like a hare in this than it does in the sky. What you normally see is this sort of parallelogram thing here, making a kind of what appears to be a bow tie underneath the knees of Orion. But for a small constellation, it has quite a lot of interesting things. It has, for instance, a globular cluster. Now, everyone thinks of globular clusters as being actually in the summer sky. They kind of surround the Milky Way, but this is an exception. It's actually located beneath, about here actually, where the, no, I shouldn't have done that, It's actually located beneath the main body of the hair, and it's well worth having a look at. But unfortunately, these days we don't have a horizon. We have a skyscraper horizon. So often people have to sort of struggle to see that far south, and also the light pollution is rather a hindrance here. So if you get a chance and there's a power cut or something, it's well worth looking out this particular object. It should be visible from Flaundon. In fact, I think I've seen it at Flaundon once or twice. I've certainly seen it from my own garden, but that was a long time ago. But it's very distant. It's actually 44,000 light years away. When you consider that M13, which is the very close one to us really, is 22 to 23,000 light years distant, yeah, that's twice the distance. So it's not particularly bright, not particularly spectacular, but you're getting the satisfaction of seeing a Messier object of a globular cluster in the winter sky, and there's not many people that can say that. Another claim to fame of this constellation is there's a star called Arleigh Porus. Now, Arleigh Porus is a blood red star. It was discovered in 1845 by John Russell Hind, and the place where he discovered it from was actually Regent's Park. Believe it or not, there was an observatory at Regent's Park at that time. It's Mr. Bishop's observatory, and he was a great. He didn't observe himself, but he appointed several observing people that worked there, and John Russell Hind was one of them. He's noted for discovering Hind's variable star, which is actually in Taurus, which is considered now to be a star that's actually just being born in stellar terms. Hence, it's flickering and stuttering as and it's surrounded by a cloud of matter. So, for a small constellation, that's quite amazing. And just to make it even more interesting, just to the side of this star here, if we go, it's a double star. There you go, Alpha Leporis, double star. It's come up and told us. It also, if you go a little bit to the side of that, you'll find that there's a cluster, little NGC cluster, and it's fascinating because you will see this because it's quite bright. A sparse collection of stars, but all these stars are oddballs. One of them is surrounded. It has got a white dwarf as a companion. One of them is a red giant. They're all a bit odd, and it's quite interesting because you can actually just see a tint of colour. Now, just moving to Orion for a couple of minutes, we all know about the Orion Nebula. It's really interesting, and I've already had my little peek at it the other night. But this star here, and I pointed this out before, that is Sigma, the little faint one. Now, Sigma is actually a multiple star, but it's so good that in small telescopes it does quite a nice job as a cluster. And they're slightly different colours. And over the last sort of couple of years, I don't know why, but I've got attracted to this and I keep looking at it. And I think, well, it's pretty good. It's well worth looking at, particularly when your telescope, as my previous one, was a bit sort of awkward to get onto things. And you could easily see that without any problems. The telescope almost stopped at it. So I got a good view of that last winter. I'm hoping to have another look with the other scope this year. So, as far as planets are concerned, well, as Peter said in his excellent talk, that if you go outside in just after sunset, you have three major planets. You've got Saturn, you've got Venus, Saturn and then Jupiter going steadily eastwards. Yeah, they're great, but unfortunately they are now pretty much out of the picture. I've looked at Jupiter recently, but it's really too low to see any proper detail. And as far as we're concerned now, unfortunately, that is really the end of the observing season on it. I've also looked at the sun, which is an interesting thing to do. I looked today actually, and there is a spot group developing, or there's roughly in the lower part of the middle of the disk. There was one solitary one there on Tuesday, but so there's something to look at the sun as well. And of course the moon is always there, and it's an interesting thing to look at, and well worth trying to spot a few craters. So I'm going to leave it at that, and we'll talk about the constellations to the east of Orion at the next session, because there's some interesting objects there as well. Thank you very much. Right.
Right. Thank you for that, Richard. Yeah. Okay, so with that, I think we've reached the end of our session for tonight, and just like to invite you to help yourselves to refreshment. Thank you all for attending. Friday night, and it's not very nice outside, but yeah, I hope the journey back is good for you. So thanks again, and see you next time. Bye.